Thanks for the invited talk. So, my name is Mujib. I'm assistant professor in cybersecurity at the University of Strathclyde. My internet might malfunction during the talk, so apologies for that in advance. So essentially, the title is Challenges and Opportunities in Cyber-Physical System Security, a physics-based perspective. So this is sort of lessons we have learned. We are working on the cyber-physical system security over the years, and essentially the observation and lessons we have learned. So the cyber-physical systems are systems which have cyber and physical components like water systems or smart grid and all the industries, Industry 4.0, all these kind of production systems. I show one example here. It's called industrial control system. This is a particular type of physical systems, which are industrial systems, right? So we have combustion chamber in this example. We have a bunch of sensors getting temperature and other values being sensed here. And we have actuators which are being controlled, which are controlling this physical process, right? This sounds like a good example of an industrial system where you have all these moving parts, and since most of the talk is focused on industrial control systems, so I found this quite helpful figure. These days, industrial control systems essentially control and monitor systems, including industrial plants and public utilities, as I said before, like water systems and smart grids. And essential components are SCADA system, PLCs, which stands for Programmable Logic Controllers, and the communication channels. So one specific example of such physical systems or industrial control systems is water treatment system. And these are especially critical for, as you can imagine, for supply of water to the nation and city and states. And also because of their importance, they have been under a lot of attacks. So one of the known attacks happened in early 2000 in Australia, where one of the disgruntled employee went around and hacked the Maroochydore water system and spilled millions of liters of water into the streets of the city. And more recently, in early last year, we saw the hackers trying to poison water facilities in Florida, in the United States, through hacking the systems of water facilities. So, as it's evident now that these water systems are being attacked actively by attackers, so there is a need of defense. So some other famous attacks, one of these I mentioned, Maroochydore, it happened in 2000, attack on sewage system. Stuxnet was an attack on the nuclear enrichment plants of the Iranian nuclear plants, which is discovered in 2010, but it might be going on for a couple of years before that. And a Ukrainian power blackout, that was also a cyber attack in 2015 and again in 2016. And as I said, Florida water hack that happened most recently. And there are more attacks that happened more recently this year and last year as well. So this is being an active, these industrial systems and all the utilities being an active target for the hackers. So definitely there's been a lot of interest in defense as well. So before I explain anything about defense, I should explain a bit about the architecture of industrial systems and the threats around it. So ICS or IT or OT, these OT technologies or cyber-physical systems, they are quite different from pure IT systems like banking systems and other database-based systems or web application-based systems. So essentially what you see here is a Purdue model for the industrial systems. We have 3 different levels in this type of model. First one is a level 0, where we have physical process. This physical process can be anything like nuclear enrichment process to water system to smart grid. We have sensors, actuators here, and then we have controllers which control the physical process. So controllers are essentially just a computer which is specific for industrial applications. We have level 1 network where we have communication between different controllers, and we have level 2 network which have communication between the human-machine interface, engineering workstation, controllers, and the sensors, right? So these are different levels I'm showing you. So these are usually deployed at the field level, for example, a plant level or a machine level. So essentially, there are many places here that attackers or hackers can inject their data, can come into the picture, right? So one possibility is hacking at a level 0 where we have sensors and controller communication. That's one possibility. Or hacking into a communication layer. We have inter-controller communication, or at the level 2. And so on. So it can also attacks can also come from physical space. So there can be physical manipulations of the sensors or the actuators, and then that ultimately can translate into a disaster, let's say. So having said that, so attack detection, essentially the topic I'm addressing just now, is a very broad in cyber physical or industrial control system security, but I'm just discussing the physics-based solutions, right? So since I'm running, we are also already running out of time, and I'm given charge half an hour later, so I'm going fast because I have to leave for another meeting. So for the physics-based attack detection, we have essentially two major components. One is system modeling and estimation, and other one is detection mechanism. We look into a bit detail of both. Before we do that, I give you a motivating example of a water system, where we have a water tank here, and we have water coming from this side, and we have outflow of the water from here. So essentially, we have a bunch of sensors. You see flow sensor here. You see motorized valve, you see level sensor, you see other pump and the flow sensors here. So there are pressure sensors and a bunch of other filtering systems as well, but this is just a small example I'm showing you. So given that we know the dynamics of the process here, so we can use the first principles to model the process. So in what that means is that if we know the diameter and the circumference of this tank, and we know the flow rates, we can estimate the rate of change of water that will be filled in this tank, for example. So this is an example of a simple water tank, which can be extended to a complicated water treatment system, which essentially then constitute of water tanks, piping, flow sensors, actuators, and things like that. So if we can find the rate of change, so this is inflow rate, outflow rate. So the volume will change. So if you have inflow and then you are taking some water out, right? So if inflow is higher, the water will rise in the tank. So this is the way we can simply figure out the rate of change of height in the water in the tank, right? So that's what we can do. But doing this you can imagine, would be hard for a bigger plant. So what we do instead is we use the control theory concepts. We use subspace system identification techniques to drive the system model rather than using the first principles, right? So this is the form of a state space equation. We call a difference equation here, where X is the system state and K+1 is a timestamp. And here X is again system state and K is a timestamp. So knowing the previous state of the system and knowing the control input, which is represented by U, we can figure out where the system will go next, right? So if I have this water level at time K, I can figure out what will be water level at K+1 if I know if the pump is running or not, right? So that's the physics of it. So the second part, this is the system modeling part. Second part is the attack detection, so which happens essentially based on the sensor data, and take the difference between the estimation of sensor data. And the estimates are coming from the system model that we have created, either from the first principles or using the subspace system identification techniques, which are well-known mechanism in the control theory. Okay, so we have this residual, right? So we have difference of sensor measurements and estimate of those. So then we say, okay, we have a distribution of this residual now. This is represented by R. And if this distribution is, we know the baseline distribution. For example, in this example, I plot a figure here. We have a blue line here. So blue line distribution is the baseline distribution of the normal operation. This is what it should be. But then I show a spoofing attack here, where the sensor data is being spoofed, and that deviation that will deviate from the normal. So so this is a very easy case, like very simple example where we have a big gap between these two, and we can figure out it's being attacked or not, right? But essentially, we want to come up with a hypothesis testing mechanism where we have a threshold, and based on the threshold, we want to figure out if it's being attacked or not, right? So these are the two big components: system modeling and attack detection for a physics-based system. But these systems have faced a lot of challenges, so especially interfering techniques, because the problem is with the physics-based modeling, and especially the techniques which use manipulation of the actuators, is that they interfere with the original process of the plant. For example, imagine it's a smart grid or a nuclear system. Nobody will allow you to do that. So essentially, most of techniques are interfering, and that's a big challenge of those. And the second problem is the number of devices under attack. So as you could have seen from the system modeling, that this depends on the sensor data and the actuator data. And as well as you saw in this example that we have a bunch of sensors and actuators together. So what happens if all the sensors and actuators are under attack? If that's the case, then your system model will not give you true data, right? If everything is under attack, what you will get is you can't use this fixed-based system, right? So that's the problem with if total number of devices are under attack. Then there are stealthy attacks where attacker can always stay under threshold, right, and then create damage. And there is lack of testbed or real systems validation, which we try to address in our work. And attack isolation problem. Attack isolation problem is something which I go into detail here, and we try to address that as well. So that's the example of attack isolation. Remember the if you remember that picture where I have flow sensors, we have actuators. The problem was that if we have a flow sensor and we have estimate of that, so these are two different lines. One is grayscale, one is more in a darker scale here. So what we see here is that this darker scale is the estimate of the data, the model from the model that we have created. That's the mathematical model. And this lighter grayscale is the real sensor data, right? So this is for the flow sensor we have just seen in an example. And this represents a residual of that. Residual is difference between the sensor measurement and the estimate of that. So we have real sensor data, estimate of that, and the residual of that, right? So hence there was an anomaly or attack here, so which can be reflected in the residual, and we can raise an alarm, right? Because it will cross some threshold and we say, okay, this is an attack. But the problem is, since the attack was only in the flow sensor, the level sensor also captures that attack. If you look at the residual of level sensor, the problem is that when there is a flow, the level should go up, right? So the level should increase, the water level should go up. Or if there is a flow outside outlet, at the outlet, water level should go down. So that is happening here. So attack is in only flow sensor, excuse me, but the water level sensor is estimate is also recording that, because this is a mathematical model, right? So if you have something being subtracted, it should be subtracted from all the equations, right? So that's why we see a downfall here, and hence we can see that this attack, which is in a flow sensor, it is also being reflected in level sensor. So this is a problem, because we are not sure which sensor is being attacked. So this is a problem essentially if we have 100 of sensors, right? If the attack is on one sensor and it is shown in 100 sensors, then it's a huge issue, because we can't isolate and localize the attack, right? And hence we can't take any recovery measures. So to study this problem, we use this testbed, which is a real water treatment system. It's a 6-stage system. It's like any modern real water system with all the reverse osmosis and these ultrafiltration filters installed in it. So we use this testbed, which also solves the problem of realistic studies, which we conducted on. And again, this is another pictorial view of how attacks happen. So we have sensor data going to controller, which ultimately affects the process. So attacker can come in like a man in the middle and modify the sensor data, right? That's our thread model. We have system model. I've explained this already. So what we are saying here is that we can estimate the state of the system using Kalman filter, and from that mathematical formulation, we can do essentially the isolation of the attacks. But it's not trivial problem. So it's quite challenging, because if you see the final equations here, you see that the Y1 being one sensor, Y2 being second sensor. So one sensor is imagine flow sensor and second sensor is the level sensor, right? So this is a problem same here that we saw here. We have attack in one sensor, it's reflected in another sensor. And now mathematically we can represent it like that. And we can't get rid of this issue because both sensors are coupled. So contribution of sensor one goes into sensor two, and sensor two goes into sensor one, right? And it makes sense, because flow, if there is flow, level go up, right? There is a physical coupling between these systems. Well, now there are solutions being proposed. One is bank of observers that says that use more than one filter, like Kalman filter on another observer, more than one, not just one. But that doesn't fully solve the problem, right? So for example, if you use bank of observers model, what happened here is that if the attack is in level sensor, then it works well. We can detect attack in level sensor here, and flow sensor is showing as normal. But if attack is in flow sensor, it also shows attack, these spikes are attacks, also shows attack in the level sensor as well. So the problem stays there. So then we propose something which is called bank of models and with the isolation model. And I skipped this algorithm, but I can explain from the results here. This slide again show you the problem. So you saw that we have attack in one sensor. So there is attack, this is attack one coupling, which is actually happening here in this flow sensor. And on the top, it is being coupled. And attack 2 is actually happening in the level sensor, and it is being coupled into the flow sensor as well. So the problem was there. And the solution we proposed is bank of models, where we say we use multiple models instead of multiple filters, right? So we have multiple mathematical modeling for each sensor separately, and in that way, and we also have a joint model. So based on that, we do this kind of voting where we have attack. If we find an attack in the joint model as well as we find attack in the isolated model, so we can isolate the sensor, right? So if joint model says attack in both sensors, and then the individual model says attack in this particular sensor, then we combine the results and we can isolate where the attack is. So this shows you the individual model for each sensor, right? So we have attack and it is not being coupled. It's just reflected in only that sensor. So attack 2 was here, attack 2 was detected here, attack 1 was here, it is detected here. Unlike previously, when attack 2 was here, it was detected here, but it was also detected here somewhere else, which we don't want, right? Um, and then this is a table where we have all the attacks on all the as I said, this is a big plant, right? 6 stages, a lot of sensors in this, and all we have done a lot of attacks on that. To understand fully, we have to follow the link to a paper which is in one of the slides, and it's on archive, by the way, it's open access. So we get very high accuracy with when we combine everything. Sometimes we get up to 100% attack detection accuracy. It's not perfect in every case, but it gives us better results. So with this, I would conclude my talk. Thanks a lot for your attention. I know I went a bit quick, but in the interest of time, I had to do that. So if you want to know about more about this work and any other related work, so please you can use this. You can scan this QR code. This will take you our Google Scholar page, and there more information on our work and this one and related work as well. So I will be happy to answer if there are any questions now.